Welcome to lecture 48. In this lecture, we look at the polynomial ring in n variables, k field. So this is R, okay, and k is a field, and this is graded with degree of xi equals 1 for all I. Okay, so a lot of arguments will go through, even if you don't assume k is a field. We could generalize this to, for example, Artinian local rings or Artinian rings. In some case, we only need that k is Noetherian. Okay, so this is not the greatest generality that I am writing. I'm writing this with so that we can revisit our computational techniques with the new, with the increased understanding of dimension, etc. We can go back to the computational techniques, and also because these now have applications in geometry. So we'll try to understand various computations that we did, etc., what it means in geometry a little bit more thoroughly. Okay, so this is what. Okay, so here is a graded now. Okay, this is a version of the graded Nakayama's lemma. Okay, suppose that M is finitely generated. Just maybe I should keep this. So by M, we will denote the homogeneous maximal ideal. Okay, and we will see this. After this lecture, or that a lot of our intuition about how local rings, a Noetherian local ring R, M would behave, sort of comes from or can be tested by working with homogeneous modules, homogeneous ideals, this maximal ideal in that ring. Okay, so this is a good example, not to just for computational setup or geometric setup, but also for us to sort of understand what would happen in the local case. Okay. This is just a meta principle, it's not a theorem, but the theory sort of proceeds in parallel. So, infinitely generated. If the homogeneous maximal ideal times M is M, then M is 0. Okay, and the proof is substantially simpler than the local Nakayama case. We'll see now. Okay, M is finitely generated. Therefore, M is finitely generated. This implies that there exists a smallest non-zero degree in. So let's assume by way of. Okay, so by way of contradiction, assume M is not zero. Okay. Since M is finitely generated, okay, there exists a D such that Mi is 0 for all I less than D and MD is non-zero. Look at a set of homogeneous generators and among them pick the smallest degree that appear there. Okay, so that is this D. This is non-zero. Okay. So let M be inside MD. Okay, but M is equal to MM. So in other words, there exists some M1 through. So these are different looking M's. This is okay. M1 through Mn inside M such that okay, M is x1 times M1 plus xn times Mn. But what are the degrees of these? Degrees of these is at least D. Degree of xi, degree of Mi is greater than or equal to D. This implies that degree of xi Mi is at least D plus 1. So this part So this part has degree greater than or equal to d plus 1, while this has degree d, and that is a contradiction. Okay, and that's the end of the proof. Okay, so we see that the graded Nakayama lemma is substantially simpler than the local version. Okay. Yeah. But the advantage, of knowing the result is that we can now redo what we did in the local case, which is the following. So the following many things in the local thing that we did. Yeah. Okay. With notation as in the lab, so M finite proposition, M finitely generated. Okay. Then there exist graded, finitely generated free modules F1 and F0 and F1, F0 and phi from such that the following sequence is exact. Which is F1 to F0 to M to 0. In other words, if M is a co-kernel of this map, this is 0. And the maps preserve degrees. Okay, this is the point, that we can just take like this. We'll prove this, but we can take like this, so that under this map, an element of degree k will go to degree k here, and under this map, same thing here. Okay? These maps preserve degrees. Okay? So prove. Okay. M and MM are graded. M is graded, so MM is also graded. Okay, so let's say M1 through MS inside M be homogeneous elements, okay, such that their images in M mod MM form. So the homogeneous, so this is the key point here. Otherwise, this is the argument as we did the same argument for finitely presented. Finitely generated is same as finitely presented over a Noetherian local ring or a Noetherian. After that, we refined that thing to say how we can construct a minimal generating set. It's the same argument, except we can now work with homogeneous elements. The images in a form R K basis. So remember, K is isomorphic to R mod M as a graded K algebra, or a graded quotient of R. Form a K basis of from a K basis of this thing. Okay. Now let E1 through ES be set. Okay. Yes, let this be a set, and let degree of EI be equal to degree of MI. Same as there are S things here, so take the same number of elements here, and now consider the free module generated by these things. Okay. It is a free module, but now it is actually a graded module because each of them is not just isomorphic to R, but the generating set itself is homogeneous. Okay. Now this can map to M. Okay. And by graded Nakayama's lemma, this would be surjective. That is, okay, that any generating set for this basis will generate. This is the same argument. Look at the image of. Maybe I should just say. Let me just say it here. So then, M is equal to the submodule generated by that. Okay. Look at the submodule generated by this. And then one can show that M mod that submodule maximal ideal times it is maximal tide M is inside the submodule plus maximal ideal times M. That's what the generating thing will say. Okay, so therefore M is equal to this. So that argument is exactly that is the part where one has to use graded Nakayama's lemma. Okay, so use graded. This is just analogous to what we did in the local case. Okay, so we get a map like this, and this map preserves degrees. Okay, so this is the first observation. Now repeat this for the kernel. And that would give us a map as we asserted. Okay, finitely generated free modules, which are themselves graded modules with a presentation map. Okay, so this is the end of this. Okay, so graded Nakayama lemma comes exactly like this. Okay. Okay, so now just some notation. This is a frequently used notation. So one should familiarize oneself with it. So M graded module. Okay. D some N some J some integer. Okay. So then by M sub J M bracket J, we mean the graded module. We mean the graded module okay with so as abstractly as an abelian group it is same as M, but what we have done is to shift its degrees. So with Mj in degree I is Mj plus I. Okay. So let's keep this, let's remember this formula. Mji is Mj plus I. The reason is the definition is this notation is slightly counterintuitive, and let's check what that means. So R minus 1 is a rank 1 free module, is a rank 1 graded free module. Whose generator lives in degree 1, okay, not in degree minus 1. That is, okay. So the notation for the formula, this is very convenient, and therefore in applications also it's actually quite convenient, but one should keep this in mind. R minus 1 means rank 1 graded free module whose generator lives in degree 1. Okay, and why is this? Why is that the notation? So if you take R minus 1 in degree 0, this is R of minus 1 plus 0, this is 0. R minus 1 in degree 1 is R minus 1 plus 1, which is R0, which is K. This is where the generator as an R module comes, and then so on. Okay. If you look at R minus 2, then if you look at r minus 1 in degree 2, you would get minus 1 plus 2, which is r1, which is the k span of x's, the k span on the polynomial ring, linear span of the x's, and so on. Okay, so this is a free module of rank 1. When abstractly as an R module, it is isomorphic to R, except it is not isomorphic as a graded module because the generators are in different degrees. Okay, so this is one thing that we should keep in mind, our notation. Okay, so so in other words, in the previous presentation matrix, okay, so back to the so M, let's say M is finitely generated, M1 to MS set of homogeneous generators. Okay, then what in the previous how we can restate that previous statement is, if you take R, then we shift by minus the degree of Mi. So this is what puts the generator in the degree of Mi. Okay, and then we take a free module S to M, and the generator here, okay, Ei goes to Mi. Ei goes to Mi. Okay, so this Ei is a basis element. That's what we defined, that has this degree. So it is R minus 1 to the Mi. Okay. So another, if I is a principal ideal, let's just say, let's take an F, let F be inside RD, homogeneous, F non-zero. Okay. Then the principal ideal F is isomorphic to R minus D as graded R modules. Remember, this is homogeneous of degree D. Okay. So, and why is that? Well, just use a presentation matrix. We use okay. So we can. So we want to present. We want to find a generating set for that one. It is generated by F itself, which has degree D. So we take R minus D, and we get a surjective map like this. Okay, and okay. So let's say that. So let's say so the generator of this, one shouldn't call it 1. I mean, it is not really 1. The generator is some module element in some degree. Okay, so let's call that basis E. Okay, so E here goes to F. That's what the map is. Okay. Now suppose that some R times F is in the R times E. R times E goes to 0, meaning R times E is in the kernel. That is, RE is in the kernel. Okay. In other words, so what would that say? That would say that R times F, this is R linear. Okay. R times F is 0, but that would imply that R is 0. Because now it's actually a multiplication happening inside R. So in other words, this is injective. Okay, and therefore isomorphism. I mean, we started with the surjective map. Okay, so this is one observation. And let's say that, let's just now consider I to be x1 square, x1, x2. Okay, this is the ideal. Then, so this has a generating set 2 of two elements, both of which have degree 2. So now we can map a free module, one generator for each, one basis element for each, okay, mapping to I, and this will be surjective. Okay, so let's say the basis element here is E1, basis element here is E2, and we may as well, we are free to choose, we may choose E1 goes to x squared, x1 squared, and this goes to x1, x2. We can choose, I mean, that's just a choice. Okay. So, but this is not an isomorphism, because the easiest way to, there are many ways. One, for example, so let's call this map phi. Okay, if we choose x2 times E1 minus x1 times E2, if you apply phi to this, okay, so x's come out because that's in R and this map is R linear, we would get x1 phi E1, x2 phi E1, so that is x2 x1 squared, minus x1 phi E2, which is x1 x2, and this is 0. Okay, so this is not surjective, this is not injective, so not injective, not isomorphism. Okay, and it's not very surprising at all, because another way to think about this whole thing is, this is a, if you invert all non-zero elements of R, now we are going outside the case of graded things, just invert all non-zero elements in R. R is a domain. This is a field. I mean, this is a this will be a rank 2 vector space over the fraction field. I will give a rank, because elements of I have been now inverted, so I will give the full fraction field, but rank 1 vector space, and we cannot have an isomorphism from a rank 2 vector space to a rank 1 vector space. So again, so we say that even after we invert elements, the kernel is non-trivial. Kernel is already, to start with, it might be non-trivial. Okay? So this is just some notation about this thing, and I want to make a definition and then just one basic property, and then more important things we will do in the next lecture. Definition. M finitely generated. So we are only assuming working for finitely generated modules. Okay. The Hilbert series of M is, okay. So this is a formal series. Okay. It is just what is called a generating function. We will not need to worry about these terminologies. What this, okay, so there's a variable t, and this is just j in z rank over k of mj. So m is finitely generated would imply that in each degree it is finitely generated over the base field over R0, which is k. So this is some number, an integer, non-negative integer. Okay, so that rank times t to the j. So we can think of this as an infinite sequence. So first of all, note that rank of mj is 0. In fact, mj itself is 0 for all j less sufficiently negative. Okay, so this starts from some value and then goes up, and it could be infinite depending on whether m itself is finite or not. Okay, but it doesn't go into minus infinity. It might go into plus infinity. Okay, so we can think of it as an infinite sequence of numbers that is captured together in a formal series. Okay, formal power series. Well, it's not exactly a power series because it might also involve t to the minus 1, t to the minus 2, etc. Okay, but in some formal object like that. So that's what this thing it does. So it sort of captures the Hilbert function. So this is the value of the Hilbert function at j. So it writes that function in terms of it as in terms of a formal series. That's all that it has done. Okay, now, but in some sense, it's easier to manipulate this than just worry about the function as such. And that's the only reason why this is preferred. I mean, this is sometimes preferred. Okay, so an immediate observation relevant here is that if 0 to m prime to m double prime to 0 is a short exact sequence of graded R mod, finitely, graded, finitely generated R modules. And so the modules are graded and degree preserving homomorphisms. Okay. Then the Hilbert series of M is the sum of the Hilbert series of the outer two. Okay, that is because in each degree, if you fix it to a degree, the rank of this is the sum of these two ranks, and then we can just prove for all j in Z, rank of mj is rank of m prime j plus rank of m double prime j. Okay. And okay, so then we are just multiplying by t to the j here. T to the j here. Okay. Then we take a sum over j of this quantity. So that is a sum over this quantity. Okay. But the point is that this is a formal thing. So we don't have to worry about convergence or any of those things. So this is formally, this is equal to sum for the quantity for j. This is for m prime tj plus this is for m double prime. Okay, so we can switch the order in which we are taking the sum. Okay, it's just a, so this is the proof. Okay, so we'll stop this lecture here, and in the next lecture we will study this Hilbert series a little bit more in detail.